A crystalline solid is defined by absolute periodicity. It's a repeating atomic motif driven across 3 dimensions by the vectors of an infinite lattice. This diagram illustrates the foundation of that geometry. A one-dimensional row of equally spaced points serves as the baseline, providing the translation interval that stacks to build higher dimensional systems. Because the physical lattice extends infinitely in all directions, crystallographers must isolate a finite bounding box, a unit cell, to mathematically describe the whole material. This presents a central geometric problem. Any continuous lattice contains an infinite number of geometrically valid unit cells that can perfectly tile space. The intuitive choice is to isolate the cell with the smallest possible volume, known as a primitive unit cell. But defining the tightest boundary around a single point often obscures the true mathematical properties of the structure. Crystallography resolves this chaos using a strict mathematical convention. We prioritize point group symmetry over minimum volume, establishing the rigid rules that ultimately govern all 3-dimensional Bouvet lattices. The primary crystallographic rule for bounding boxes is exact. The chosen unit cell must be the smallest repeat unit, whose delineating vectors run parallel to, or perfectly coincide with, the highest symmetry directions of the lattice. Look at this animated 2-dimensional rectangular net. The immediate instinct is to draw a primitive oblique cell containing exactly one lattice point, bounded by acute and obtuse angles at its corners. This technical drawing compares those primitive cell labels, A' and B', with a larger choice, a centered rectangular cell, delineated by vectors A and B. The primitive oblique cell is mathematically rejected. Its diagonal boundary vectors completely ignore the orthogonal mirror planes that define the rectangular lattice. The centered cell is the correct choice because it aligns its vectors directly with those mirror planes, capturing what is classified as 2mm symmetry. Even though we selected a larger unit cell with an extra lattice point in the center, the underlying coordinate geometry remains mathematically invariant. The dimensions of the primitive cell can be calculated entirely from the scalar relationship of the centered cell's edges. The symmetry of the lattice exists regardless of how we draw the boundary box. Our choice of unit cell solely determines the clarity of the mathematical framework we build on top of it. By making symmetry the primary selection criterion, non-primitive centered cells become a mathematical necessity for capturing a lattice's true structural class. This chart displays the full numbered array of the 14 Bouvet lattices. Expanding the symmetry rule into 3 dimensions strictly limits all possible periodic arrangements to these specific forms. The 14 configurations distinguish between standard primitive cells and centered variations, including cells centered on a single pair of opposite faces, on the body center, or across all faces. This prompts an analytical test. Can these 3-dimensional centered lattices simply be mathematically reduced to primitive cells to save volume without violating our symmetry rules? This source image shows a monoclinic lattice centered on the B faces. We can mathematically redefine the C vector. By taking -1/2 of A plus 1/2 of C, we calculate a new dashed vector, C', forcing a perfectly primitive bounding box. This specific transformation is valid. The monoclinic system requires the angle beta to be oblique, and our new angle, beta', meets that requirement. Therefore, a B-centered monoclinic cell reduces perfectly to a primitive one. This demonstrates the exact same reduction test on a C-centered monoclinic cell. Look closely at the resulting base vectors. Monoclinic geometry demands the A and B axes remain orthogonal, but the internal angles of this new dashed cell deviate from 90 degrees. Reducing the C-centered cell destroys the defining orthogonal relationship. This mathematical failure proves that the 14 Bouvet lattices are an exhaustive, irreducible set. Centering is maintained specifically because it is required to preserve symmetry. This projection shows a single primitive orthogonal unit cell displaying the internal trace of the 1-1 plane. We are shifting from the exterior boundaries of the cell to the continuous internal geometry of intersecting planes. By applying the lattice's translation operation, that single plane generates an entire continuous family of equidistant parallel planes, stretching infinitely in all directions. This diagram displays that continuous series of parallel planes, each separated from the next by a precise perpendicular distance denoted as d. In classical notation, Miller indices are kept prime to one another, but for X-ray diffraction, we adjust this rule. We allow the indices H, K, and L to contain common factors, allowing us to describe fractional internal planes subdividing the unit cell. A fractional plane maps exactly within its parent spacing. The 2-2-0 planes have half the spacing of the 1-1-0 planes, meaning alternate planes coincide perfectly. Mathematically, the distance to the NH, NK, NL plane is the parent distance divided by n. An external crystal face always uses prime indices. Macroscopic external observations can only reveal the geometric shape of the material. They cannot dictate the physical size of the internal unit cell. As these fractional planar families overlap infinitely across 3 axes, calculating X-ray diffraction angles in real physical space quickly becomes a tangled, overwhelming problem. To solve it, we execute a radical coordinate shift. We establish the reciprocal lattice, an inverted mathematical space designed specifically for diffraction geometry, mapping infinite 2-dimensional real space planes into singular, 0-dimensional points. We project this by drawing a normal vector perpendicular to a planar family. The distance to the reciprocal point is inversely proportional. d star equals k divided by d. Using orthogonal dot products, where mixed scalars equal 0, we sum these vectors to locate any exact point. The reciprocal lattice provides a rigorous coordinate inversion. It systematically takes the chaotic, overlapping planes of direct space and translates them into a clean, entirely navigable grid. Unit cells are chosen strictly to lock in structural symmetry, providing a highly rigid vector framework in direct space for our analysis. By taking that framework and mapping it inversely, we create a mathematical dimension where complex physical diffraction effects simplify into basic geometry. This inversion yields equation 2.16, the ultimate crystallographic tool for calculating interplanar spacing, regardless of the original crystal system. The final geometric size of this reciprocal unit cell is scaled by the constant k, which can be configured as a standard unit of inverse length, or precisely tuned to the wavelength of radiation used in your specific X-ray experiment. This reciprocal geometry maps the infinite complexity of real lattice planes into an elegant grid of discrete, navigable points. It provides the essential mathematical translation layer that allows us to decode the atomic structure of the physical universe.